The last lesson on esters was esterification, and there were 3 methods. I'll review these shortly, but today I also want to talk about hydrolysis. So it's the undoing of esterification. Okay, so you should be familiar with the 3 methods to make esters, and you should be able to state the advantages and disadvantages. Okay, so the first one is your standard carboxylic acid and your alcohol. So you get your ester and water. It's a condensation reaction, that type of reaction, because you get a small molecule like water. And you need to note that this is reversible. It's catalyzed by concentrated sulfuric acid. Another method is to use acid chlorides or acyl chlorides, as they are called, and this time it's an irreversible reaction, and the byproduct is hydrogen chloride or the hydrogen halide, depending on whether it's bromide or iodide. Okay. And the other reaction you can use is the anhydride, the acid anhydrides. So this one also is irreversible. You get your ester and you get the carboxylic acid. So if we review the 3 methods, so this one is reversible, so it's an equilibrium. I'd rather say it's an equilibrium. Therefore you get a lower yield. The conditions are mild, okay, so that's an advantage, and it's done under reflux. This one is much more violent reaction, but it's irreversible, okay, and you get HCl, which is a corrosive gas, so that could give a problem in terms of waste. And the last one, the acid anhydride, the alcohol, that is irreversible, and therefore you get a higher yield and the conditions are mild. It's also under reflux. Okay, so that's the 3 methods to do esterification. The mechanism for esterification is nucleophilic addition elimination. So here I have got an acyl chloride, but it could be a carboxylic acid or it could be acid anhydride. It's the same mechanism. Okay, so the idea is that the alcohol acts as a nucleophile because oxygen has got a lone pair of electrons on the alcohol has got a lone pair of electrons on its oxygen atom, and it's going to attack the carbonyl group. So that's the carbonyl group. C double bond O is called a carbonyl group. Because it's a polar bond like that. Okay, so that mechanism should be familiar to you. You form a coordinate bond between the oxygen and the carbon atom. So that pair of electrons goes onto the oxygen atom, so you're going to have a positive charge on this oxygen and a negative charge on this one. So that's your nucleophilic addition part. Okay, then what happens next is that lone pair of electrons goes between the carbon atom and oxygen atom, so is now shared, so the oxygen atom loses its negative charge, and that pair of electrons between the carbon and the chlorine atom, that bonding pair of electrons goes onto the chlorine atom, and you form this species and Cl, and afterwards this loses a proton, so it loses H, so that lone pair of that bonding pair of electrons goes as a lone pair on the oxygen atom, then therefore it loses its charge, and you got H plus and then Cl minus to form HCl. Okay, and your ester. So as I said, it doesn't matter what this is, it's the same mechanism. Yeah, here you could have OH, as the case of carboxylic acid, or you could have your acid anhydride. It will be the same thing. The ester will be this form. It will be the same. Obviously, the byproduct is different. Here is HCl. If here you have OH, then the byproduct is H2O, and here if you've got the acid anhydride, then the byproduct is the carboxylic acid. So hydrolysis, so it's splitting up, using water. So it's the reverse reaction of esterification. So you've got your ester, you add water, and then you get your carboxylic acid and your alcohol. Okay, so if I've got ethyl ethanoate and water, you get ethanoic acid, and ethanol if you got methyl propanoate, and water you get propanoic acid and methanol. Note that it's reversible reaction, okay? And for propyl methanoate and water you get methanoic acid and propanol. And finally, that is so that's the displayed formula. So you can do the same using water or dilute acid. The reaction with water is slow, but that's about it. Okay, and it's in equilibrium. So another way of using or splitting the ester, getting the hydrolysis going, is to use dilute alkali, so like sodium hydroxide or potassium hydroxide. So it's the more conventional way of using the ester, doing hydrolysis. The ester is the only reflux with a dilute alkali like sodium hydroxide solution or potassium hydroxide. So the advantages of using dilute acid or water hydrolysis is that the reaction is irreversible, and then the products also are easier to separate because you get a salt and your alcohol, so it's easier to separate than a carboxylic acid and the alcohol. But as I said, you form the salt solution and your alcohol rather than the carboxylic acid itself. So I'll give you a couple of examples to illustrate that. So we've got your ester, yeah, and sodium hydroxide, and that's what I mean. You form the salt, so you form your sodium carboxylate, if you like, and your alcohol. So if you got ethyl ethanoate and sodium hydroxide, you form sodium ethanoate and ethanol. And note that the reaction is irreversible. That should be a full arrow. And the same for all of the others. So you get the salt, okay? You get the salt, and your alcohol is very easy to separate it, because this will be much easier to separate than a carboxylic acid and alcohol. So if you got methyl propanoate and sodium hydroxide, you get sodium propanoate and methanol. And likewise, if you got propyl methanoate, you react it with aqueous solution of sodium hydroxide, you get sodium methanoate and propanol. So this reaction is very useful, and indeed it's been done for hundreds of years, reacting sodium hydroxide, or also called lye, Lye, and fatty acids like animal fats or vegetable fats, and then we make soap, and so that's also called saponification. Okay, so if you've got large esters, like from animal or vegetable fats, yep, and then you heat them up in concentrated sodium hydroxide solution, the same reaction happens as with smaller, simple ester molecules. And then what you get is the salt of a carboxylic acid is formed, okay? And these are it's a soap, okay? And in the case of esters, esters from animal fat or vegetable fat, you also form glycerol, which is propane 1,2,3-triol, and that's very useful in cleaning products. And so this is your fatty ester, sometimes it's called. You can see that that's your ester. Yeah, so that's your if you hydrolyze here, yeah, you're going to get your ester, and then you're left with propane 1, 2, 3 triol. Okay, so I think the next slide will show you exactly. Okay, so if you hydrolyze it, you're going to split it with water. There you get your carboxylic acid. So this is the carboxylic acid here. This is the carboxylic acid here, and this makes the carboxylic acid here, and then you're left with your propane 1, 2, 3 triol. Okay. Now, if you use sodium hydroxide, then you get the salt, yeah, and that is, if it's got a very long chain, then that makes soap. That is soap. Okay. And soap, basically, that used to be part of GCSE until a few years ago, and I thought at the time it was interesting, but they decided to get rid of it. So basically, the soap, yeah, it works because it has got a long tail that is hydrophobic, that doesn't like water, and an hydrophilic end. So that end dissolves in water, okay, and that one will help dissolve things that are not dissolving water. They are likely to be dissolved in hydrophobic in the hydrophobic tail. So these ones, these soapy molecules, they form little spheres, yeah, and in those little spheres, that is where all the dirt dissolves, because it doesn't dissolve in water, but it would dissolve in this. Okay. Otherwise, what would happen is that all the dirt will float on top of the water, and especially if you got a washing machine and you drain that water, then at the end, so the water will leave the washing machine, and it will leave a thin layer of dirt on top of the clothes, so they wouldn't be cleaned. Okay. Anyway, this is all the surfactants, surface active agents. We might just talk about it a bit later when we do when we talk about amines, because they also form surfactants. So that's I find that type of chemistry quite interesting. Anyway, soaps, they've got a hydrophobic tail and a hydrophilic head. So hydrophilic likes water, hydrophobic doesn't like water. Now that brings me into biodiesel, because biodiesel is formed from the hydrolysis of esters from vegetable oil. So biodiesel, like maybe 10 years ago, that was going to be the future of reducing our dependence on hydrocarbons, which obviously you need to grow the crops, and if you grow the crops to burn it as a fuel, that means that there could be food shortages. It certainly wasn't the greener option, because you also need pesticides to grow healthy crops, and fertilizers, and lots of water. So it takes away lots of useful resources, and we don't eat it, we just burn it as a fuel. Okay, anyway, it's part of syllabus, so I have to talk about it. Right, so you're going to tell me that you can't just put these oils in the engine, because they look like this. Okay, so these are very large, very, very large molecules, and therefore they will have a high melting point. So that's not very good, because you won't be able to vaporize it, so that you can eventually burn it, so it won't be very flammable. nothing to do with vaporizing. So you won't be able to burn it. It will be not very flammable at all. So that's not very good fuel if it's not flammable. Plus, it's a very, very large molecule, as you can see. So it will have a high viscosity. So it won't flow very easily, you know, from the tank and into the engine. So that's not good. So for this, you need to break those molecules. Okay. So they break them, and they make esters out of them. And the reason why they make esters is because those esters, they're smaller molecules. These 3 esters are smaller than this large one. And they don't want to get the carboxylic acid, because the carboxylic acid will have a much higher melting point and will be much more viscous. Okay, so this one, by replacing the hydrogen atom by a methyl group, it reduces its intermolecular forces. Okay, because this one hasn't got hydrogen bonding, whereas a carboxylic acid would. Okay, so basically they react this with sodium hydroxide to get the hydrolysis, and then they add methanol. It's one pot chemistry. Okay, then you get glycerol, and you get your ester there, and these are insoluble. So you get 2 layers. So they are very easy to separate. Okay, and then you get your fuel, because that's quite flammable. Okay, and that's what they call biodiesel. So that biodiesel is not a hydrocarbon. What it is an ester. Yeah, a fairly large ester. So here you typically have 8 to 12 carbon atoms. And sometimes, most of the time, that chain is unsaturated too. Yeah, because you get it from vegetable oils. So yeah, so that shows that's your ester part. Your 3 esters at the end. Yeah, okay. And your ethanol, that's the methyl group for the ester. And then you're left with your glycerol, also known as propane 1,2,3-triol. Okay, as I said, these 2 products, they are easy to separate. So that you need to know about biodiesel. Basically, those chemical reactions. Usually R1, R2, and R3 are the same. Okay. R1, R2, and R3 are the same. So, to summarize, hydrolysis of esters. So you can use an acid or aqueous just water, but the reaction is slow and reversible. Or you can use alkaline solution using sodium hydroxide. Yeah, and that's the type of saponification, because that's a chemical reaction to make soap. And you get the salt of the carboxylic acid. Okay, and the reaction is not equilibrium. For this one, you get the carboxylic acid, and it is in equilibrium. Okay, that's it for hydrolysis. Thank you.